Hello CS11, welcome to lecture 15. For lecture 15, we will be talking about generators. So first things first, I hope you are still practicing. As of now, the following should be available to you. So practice sets 5 through 9, as well as lab exercises 3 and 4. So the coverage of Hope 2, Hope 2 is going to be from all of the links, the contests over here. So make sure you go through them in order to prepare for Hope 2. Alright, so generators. What is a generator? So for some of you, we have seen generators in some of our previous classes. So here, remember that when we introduced, say, lists, we said that we can do something like list of x for x in range 5, and this will give us 0, 1, 2, 3, 4. Now, we also said that aside from that, another way in which we can make a list is by doing this instead. So use brackets. So if we do that, we get the same list. So back then, I mentioned that you can't do this with tuples. So even though you can do this, this will make a tuple with 0, 1, 2, 3, 4. If you try to remove the tuple here, instead of making a tuple, this will make this weird thing. So as you can notice, this is a generator object. So generators are what we are going to talk about in this lecture. So what is a generator? It's essentially a one-time use sequence. So even though, let's say, we have this list, if we have a list, we can use that list several times. So we can index it, we can show the entire list multiple times. Generators, on the other hand, are one-time use. So for generators, there is really only one thing that you can do with them, and that is to get the next element. What do I mean by that? So if G is a generator, to get the next element, you do next G. So let's say I have this is x for x in range 5. So now I have a generator. Notice that I can't index this, so generator object is not subscriptable. So to get elements, I have to use next. So next of generator is going to give us 0. Okay, how about if I do it again? So now, after the second next, I get 1 instead of 0. If I keep repeating this, I'll eventually get 0, 1, 2, 3, 4, or all of the elements of the generator. So if there are no more elements, then something happens. An exception is raised. Remember exceptions from lecture 11. These pop up whenever you do something that causes a problem, or Python has a problem with what you're doing. So if we try to do this one more time, we will get a stop iteration, which essentially means you're done going through all the elements of the generator. If I do this again, it still gives me stop iteration. So notice that here, since I already used these elements in these lines, I can no longer have access to them again. So my generator is still this same generator, but I can no longer get elements from it. That's what makes it single use. You can only retrieve these elements once. Okay, so note that this is imperative. Notice how here, when I called next of gen multiple times, they gave different results. So as you can see, referential transparency doesn't really apply here. We can't just quote-unquote substitute yung next gen with a particular value, since it goes through all of the values of a sequence. So yeah, it's an imperative concept, which is why it's in Hope 2 instead of Hope 1. So how do we make our own generators? So you've already seen that one such way is by doing something like this. So if you have this, you can get the elements like so. So how would you, aside from just a comprehension like this, how do you typically define a generator? To do that, we'll have a new keyword, yield. So inside a function, or something that starts with def, use yield. So what does that look like? So let's say I have this function here that has 4 names. So this is a function, and inside the function body, I am yielding these 4 names. So let us have that. So once we have that, what can we do with this? So let's say we have this generator. In order to use it, we just call it like a function. So notice how the def part here is the same as a ordinary function. So in order to actually get a generator out of this, just call it. So g1 is equal to members, g2 is equal to members. So now if we have that, we can try to look at what happens if we retrieve the elements from these generators. So let's start with this. If I have next of g1, what this is going to do is momoy. So it's going to give us the first element of the first name over here. So if I do that again, I get Midori this time. So momoy first, then Midori. So these two, notice how it goes through these two names in these two calls to next. So what if I call next of g2 instead? So instead of g1, again, I now do it for g2. So try to think about it for a few seconds before I run this. So if I try to do that, I get momoy again. So since g1 and g2 are made by calling members multiple times, these refer to different instances of the generator. So this is one generator, or one copy. You can think of it as one copy of this sequence of names. This is another copy of this sequence of names. So that's why this second generator, if we run next here, that's why it starts at momoy again. So if I go back to calling next of g1, this is going to give me Aris. So since we already called next of g1 in these first two calls over here, calling it a third time is going to give us the third name that it yields. So each yield corresponds to a certain value that you want to get from a generator. So momoy first, Midori, then Aris. So that is what this sequence of lines outputs. Okay, so yield actually kind of works like return, but instead of exiting the function, it doesn't exit the function. So remember that for an ordinary function, let's say f of x, return x plus 1. Whenever we call this function, once it reaches this return statement, it's already done. So remember in our discussion of the call stack, we said that whenever we hit a return inside a function, it gets popped off the call stack. So its stack frame gets removed from the call stack. So for generators, yield does not exit the function, unlike return. So what happens here is it just stops the execution of the generator temporarily. That is why we can call next here multiple times. Every time you call next, what is happening is that it goes on until it reaches a yield. Once it reaches a yield, it stops first, then waits for the next time you call next on it. So it starts here, then once it yields, it waits for the next call to next. After this next call, that's when it runs the second yield, and so on and so forth. So yeah, this is different from return. So if Python sees that inside a function definition, something that looks like a function, there is a word yield, then Python will automatically know that, hey, this is a generator, not an ordinary function. So even if I have a complicated function like this that just does random stuff, if I yield somewhere, let's say I have this, if I try to get what f is, well, it says that f is a function. So if I have g is equal to f of 1, it sees that Python knows that this is generating, or this is a generator. Or if we call it, it will give us a generator object, since it has a yield over here. So yeah, once we call a generator and we try to print it, it will give us generator object at something. Okay, so since yield and return behave differently, unless you really know what you're doing already, try not to mix yield and return in the same function. If you're not yet comfortable with what's happening over here, and in the later examples, try not to use them in the same function yet. Okay, so we said earlier that generators are one-time use. So to demonstrate that, let us try to use it here. So G is members. So one thing you can do with a generator is, well, since it's a sequence of values, there's nothing stopping you from putting that inside the list function. So if I have list of G, this will give me the 4 members over here. If I do that again, here in this third line, if I do it again, you'll see now that instead of giving us this, it now gives us an empty list. Why is this so? This is because generators are one-time use. Once we generate, or once we feed the generator into this list function, all of the values inside this generator, yung 4 names over here, are already gone. They've already been consumed by this first call to list. So when we make the second call to list, all of the names here are no longer there. So generators are one-time use. Okay, so most of the sequences that we've encountered so far, like tuples, strings, they are not one-time use. So if we have sequence is 1, 2, 3, 4. Let me use the same names. That is user. So if I have a tuple instead, then I wrap that inside a list function. I get these same names. If I do it again, I still get the same names. So sequences like tuples, strings, as well as lists themselves are not one-time use. You can use them multiple times like this. Okay, so if that's the case, if doing list 2 times on a generator will only populate the first list, how do we also populate this second list? Well, to do that, we'll go over that later. But to make a generator, so if we have list to make a list, tuple to make a tuple, frozen set, as well as dictionary to make sets and dictionaries, how do we make generators? So to make generators, we use iter. So let's say I have sequence. This is my sequence. If I want to make a generator out of this sequence, I have to wrap it around iter. So iter sequence now gives me something called a tuple iterator object. So if we assign that to a variable, And now we do list of G. This still gives us the same thing. If we do it again, just like before, for this first for these first few lines, if we do it again, the second list is no longer populated. So this also gives us a generator. It's not exactly a generator since, as you can see here, it's called tuple iterator instead. But if we try to call next on it, just like an ordinary generator, it still gives us the values in sequence. Okay, alright. So notice that if we try to get sequence again, even though we wrapped sequence inside iter, sequence itself is still intact. So you can wrap a sequence inside iter, and the sequence is still going to contain the same values, even if you make generators like this. Okay, so sequence still gives us the same sequence of values. Alright, so okay, that's nice to know and all. But why do we have generators in the first place? What's the point? If we already have tuples, lists, sets, and all of that good stuff, why do we even care about having some weird function like things like these? Well, for one, they can be used in comprehensions. So what does this mean? So here, if I have this, let me change this to this instead. So if I have this, so this will give me, this is the generator from a while ago. If I do this will give me these four values. So notice that this is pretty much a normal comprehension, except the sequence we're getting from is a generator. So okay, aside from that, they can also be used in loops. So we already went through loops several lectures ago. So if we have for name and members, we can have something like print, then let's say name, then let's have a string over here. So if we do that, we have 4 strings over here. So okay, that's nice. We can use them in comprehensions. We can also use them in for loops. But still, we can also do this with standard sequences. So if I have the same names and I use that in a comprehension for name in mems, that still gives me the same sequence. If I do the same for loop, that still gives me the same for print statements. So we can still do what we did here using a standard sequence. So okay, what else can we do with generators? Okay, so we know that Python keeps calling next, or how Python implements it is that it calls next until stop iteration is reached. So you will see more relevant uses of generators later, even though they might seem kind of useless for now. We're going to see later, as well as in later lectures, why we want generators in the first place. Okay, let us look at more things, for more code blocks that use generators. So let's say we have this. So I have gen is equal to members. So if I have a for loop for name in gen, print a then name. If I try to run this, what is going to come out? Try to think yourself first before I run this. Okay, so if I try to run this is going to give me a as well as the names. So it does pretty much what we expect. Now if we try this second set of lines, so for name in gen, print v then name. If we do this, what is going to happen this time? Okay, if we try that, nothing happens. So why does nothing happen? Remember that generators are one-time use. So since we already used the generator in this first for loop to get these 4 prints over here, if we try to use it again, the generator is going to be empty since it already got consumed inside this for loop. So since it's empty now, this for loop has nothing to iterate over, which is why nothing appears over here. So again, the first loop consumes the whole generator. So even though generators are one-time use, or because generators are one-time use, we don't really recommend setting them to variables, since, well, the reason why you use variables is to use something multiple times, and generators are not something you use multiple times. So try not to actually set generators to variables. Okay, alright. So let us look at this. So this is something that makes a generator. So given an input for v in range n, so it goes over all numbers from 0 to n minus 1, and it yields the squares of those numbers. I believe this is the first item in practice set 7. So you're given, you have this, let's say you have this, you're given an integer, then you yield the squares from 0 squared all the way up to n minus 1 squared. So this is a function-like thing that makes a generator. So if I have some squares of, let's say, 5, this is going to give me a generator. And now if I use next, let's say I set this to gen is equal to sum squares of 5. Again, try not to set them to variables unless you're sure you're only going to use it once. So if we try to call next, we get 0, 1, 4, 9, then 16. So as you can see, this gives us the squares from 0 squared all the way up to 4 squared. Okay. So if we try to, we already know that if we try to print this out, we're going to get generator object here. So if we try this instead, so let us splat that, sum squares 5. Now if you just splat it like this inside interactive mode, that's actually a syntax error. You have to wrap that inside something. So if I have print, then sum squares of 5, this is going to give us 0, 1, 4, 9, 16, the same values that we got over here. So yes, you can also splat a generator or the values of a generator into other functions. Okay, so this thing is, well, that is looping over something and yielding something based on each item in the loop. That's common enough that there's actually a Python way to write it, which is what I showed at the very beginning. So you can also write what we had over here using g is equal to x squared or v squared for v in range 5. So this will give me the same a generator that generates the same values. So if I call next g multiple times, it will give me the same values. So this thing actually makes a generator. So if we use parentheses without putting anything before it, what this is actually making is a generator. So formally, we call this a generator expression since it's an expression that evaluates to a generator object over here. So we can do the same thing. If we have G is equal to this, list of G gives us a list with those values. If we call that again, it's empty since all the values have been consumed. So just like any normal comprehension that we've learned from one of the lectures in Hope 1, you can also do other kinds of comprehensions to make a generator. So if I have G is equal to x plus y for x in range 5, for y in range 3, if I try to get next of G now, this is going to give us 0, then 1, 2, then 1, 2, 3, 2, 3, 4, then finally 3, 4, 5. So just like with how we used comprehensions in Hope 1, the first 4s are the more major ones. So x, it starts by setting x to 0. Then once x is set to 0, it iterates over each possible value of y. So 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 2 is 2. So that is how this generator works, just like a normal comprehension. If I wrap this inside brackets instead, this would give me a list containing the same values 0, 1, 2, 1, 2, 3, and so on. Okay, so let us try to make our own generator. Here, let's try to make the range function without actually using range. So given a starting value and a stopping value, try to make a generator that generates everything from 3 all the way until before 7. Okay, so this is a generator. So the way we define it is just like an ordinary function. So my range, then it takes in A and B. Then we have to fill in this part. So if we try to think of the simplest way we can express what we want, it looks something like this. We want to yield A, since that's the first value we want to yield, and this is a generator, so we have to yield instead of return. We want to yield A, then A plus 1, and A plus 2, then all the way until yield B minus 2, then yield B minus 1. So we want our generator to do something like this. So how do we actually turn this into something that works instead of just putting all of these lines over here? Well, one thing you can notice is that this is essentially the same as for, let's say, value in my range A plus 1 B. So yes, we're using recursion here. This part is just equivalent to my range starting at A plus 1, then ending before B. So for V in my range A plus 1B, what we do is yield V. And there, that is actually what we do. So this is how we would implement this. There's a minor thing that we have to check. If, for example, A is equal to B or something, or if A is greater than or equal to B, then that means you have nothing to generate since B has to be exclusive. So all we have to do is check that. So if A is less than B, then that is where you actually put all of this stuff over here. If otherwise, you don't have anything to generate. So this is what we put over here. So if I have gen is equal to my range, then 3, 7, And for value in gen, print value. This will give us the values that we expect. So that is how you make this generator over here. So this is another way to do it. If a is greater than or equal to b, you want to do nothing, so you can pass instead of doing anything. Otherwise, same thing as we did over here. So notice that even for generators, wishful thinking is still very helpful. So here, we see that by calling my range using a plus 1 and b, that gives us the rest of the values that we need to generate. And once we have these, all we have to worry about is yielding a. So yield a, then yield everything inside this other range. Okay, so again, we did this just to demonstrate that we can make our own range if we do something like this. But in practice, please just use the ordinary range function. Okay, let's make another one. So here, we have a sequence. Then we just have to duplicate each element of that sequence. So let's make a generator. Define duplicates. Then we have a sequence. Then for each element of that sequence, we want 2 copies of that element. So if we think about it in the unrolled way, we would have something like x is equal to sequence 0. This is the first element of the sequence. Then since this is a generator, we have to yield it. So yield x. So that gives us 1 copy of the element. Since we want 2 copies, there's nothing stopping us from just yielding x again. So after yielding the first one, yield another copy of x. So we can do the same thing for the next element. So x is equal to sequence at 1, then yield x, so on until you reach sequence, the last element, yield x. So this is the unrolled version of what we want to do. To get the rolled version, as you can imagine, we have to iterate over for x in sequence. What we do is the loop body. So yield x. And yeah, that is actually how we make this generator. If we have for name in duplicates, then we give it a sequence. So if we give it a sequence, it now gives us each element of that sequence, but twice. So this generator does what we want it to do. So that is how we make this generator. Alright, let's move on to this one. So here, we basically want to enumerate the elements of a sequence. For each element, we add a corresponding index to that element. So enumerate from takes in a sequence as well as a starting value. So this is where it starts counting. Okay, let me add a colon there. So how do we want to implement this? Well, the first thing we want is, if we look at what we're going to do to the first element, we have x is equal to sequence at 0. Then here, since we want to pair up start with x, we have yield, then start x. So something like this. We can do the same thing for the second element, but we want to pair it with start plus 1 instead of start. So we can increment start by 1. Again, this is equal to start plus 1. So this is the same thing. Then once we do that, we can do x is equal to sequence 1, then do the same yield. yield start x, then increment again. So this is the unrolled version of what we want to do. For the rolled version, this would be for x in sequence, yield start and x, and start plus equals 1. So we just rolled the loop body, and we end up with something like this. So if we have another set of names, okay, we have another set of names and we enumerate in that sequence. So for I and name, and enumerate from then our sequence as well as a number to start at, print I and name. This will give us the elements paired up with their corresponding indices. So this is how you would make this generator. Again, when you're making a for loop, you do the same thing. Start from the unrolled version, then roll that back up into a rolled version. Okay, so something like this. So most of you are probably familiar with the enumerate function by now. So this essentially does the same thing as the enumerate function. Okay, so there, these two things pretty much do the same thing. Okay, so how about this? So remember that we had this in one of the first few lectures for the second arc when we were discussing for loops. So given a string, how many consecutive letters are there? So assert this. So again, this is 3 because there are 3 pairs of consecutive letters over here. So if we want to implement this, we can actually also implement that using generators. So how can we implement this using generators? So it looks something like this. There is a thing called sum, which basically gets the sum of everything that you feed into it. So sum of 1, 2, 3 is equal to 6. You can also give sum a generator. So if we have my range from a while ago, 10, then 20, this will give us the sum of 10 plus 11 plus so on, all the way until 19. So sum also accepts generators. So here, what's happening is that to define equal consecutive of a sequence, what it does is return sum. So 1 for I in range length of sequence minus 1 if sequence I is equal to sequence I plus 1. So something like this. Remember that the for loop version of this, if the for loop version looked something like for I answer is equal to 0 for I in range length of sequence minus 1. If sequence I is equal to sequence I plus 1, we incremented the answer. So the for loop version looked something like this. So we can also express that using a generator in this way. Basically, we're filtering out the indices that satisfy this property using a sequence with 1s in it. So we get a 1 every time we have an I that satisfies this condition. And if we add up all of those 1s, that's the same thing as if we started with 0, then we incremented 1 for every time it satisfied this condition. So these two do the same thing. So again, sum receives any sequence and returns the sum of everything inside of it. Okay, lots of other built-in functions that we've introduced also receive generators. So min, max, sorting, something, joining, then the standard functions tuple, list, and frozen set. Okay, so how about this? We also had this in one of our previous lectures. Given a string, reverse the individual words. So let's say, okay, here. So again, most of the built-in functions that we know also take in generators. So there's nothing stopping you from putting inside a comprehension that makes a generator inside these built-in functions. So here for this call to join, space dot join, then inside join we have a generator over here. So yeah, this basically for each word in text.split, remember dot split splits this by spaces. So this becomes hey dude dot split becomes hey and dude. So if we have word, then we reverse that word for word in hey dude dot split. This is a generator. If we call next on that generator, or if we iterate over it, for new word in, then we print out that new word, we are going to get the values that we want. And in the end, we can just join them with spaces. So that is how we make, how we use generators in built-in functions. How about this? A generator that goes through all suffixes of a string. So typically, how we did that is something like this. So let's say loop, then suffixes, then we're given a string. How we would normally do it is have a list over here, then for I in range length of s plus 1, what we would do is append, then answer, then I all the way to the end. So something like this, or answer.append. So we append a suffix at each iteration of this for loop, then return answer. This is how we would conventionally define it. I think I have an extra parentheses here. So if we have loop suffixes of a, b, c, d, e, this gives us, oh, nothing. It should be s. There. So loop suffixes of a, b, c, d, e now gives us the suffixes of this string over here. If you have a for loop that's building a list like this, to write it using yield instead of return, all you have to do actually is for I in range length of s plus 1, you just replace the loop body as if you were yielding each element you were putting inside the list. So yield s, then I onwards. That's the generator version of this. So if I have list, then loop suffixes a, b, c, d, e, this will give me the same results. So instead of building stuff into a list, you can yield the elements directly. Since yield does not completely stop the function, it just temporarily stops after this call to yield, you can use it like this. Okay, so same thing for most of the other things that we've implemented. So if I have partial sums, if I want to get the partial sums of a sequence, so again the partial sums are the sums of the prefixes of the sequence. So the empty prefix has sum 0. If we add 3 to that, that becomes 3. If we add 1 to that, that becomes 4. 4 to that to become 8, and so on and so forth. So how we would implement that is that, well, we have to yield 0 first, or alternatively, let's say our current sum is equal to 0. So we can yield the current sum since this is the sum of the empty prefix. Then for x in sequence, what we can do is current sum plus equals x, then yield current sum. So our function, our generator, looks something like this. So if I have list the partial sums of 1, 2, and 3, oops, I missed this. So this will give me 0, then 1, then 3, then 6. This is how you get the partial sums using a generator. Okay. So again, we yielded at the start here because the empty prefix always has a sum of 0. Okay, how about if we want to filter things out? Remember that we said that comprehensions are also capable of filtering certain elements out. So, if we have defined all events of a sequence, the way we do that is for x in sequence, if x is even, then we yield that element. And that's essentially it. So we're just checking if each element is even, then if so, that's when we yield that element. So list all evens, let's say range 1 to 20. This will give us the even numbers from 1 all the way until 20, before 20. So it's kind of the same as a comprehension. So yeah, using a generator expression like this, or a comprehension, is the better way, or the more simple way to write this, but this kind of pattern is also valuable to learn since you might use it for more complicated problems. Okay, so back in the loops lecture, we said that there seems to be a relationship between loops and comprehensions. By now, you should notice that aside from comprehensions and loops, they are also related to generators. So what is the relation between these three things? Okay, so let's start with comparing generators and comprehensions. Well, the news is all of the comprehensions that we have been discussing so far don't actually exist. So when we said tuple comprehensions all the way back, like this tuple comprehension, we were actually just lying to you. These don't actually exist. What's happening here is that we have this generator and we are passing that generator into a tuple function. So back in Hope 1, we just called these tuple comprehensions because we didn't go over generators yet. Now that we're going over generators, now you know that, well, what's happening here is that you're making a generator, then you're passing that into the tuple function. That is what is actually happening under the hood. So again, the tuple consumes the generator and collects the elements of the generator inside a tuple. So all this time, throughout Hope 1 and the first few lectures of Hope 2, we have actually been working with generators. Whenever we were writing something like some function, then something for something in something, we were already making generators. So similarly, aside from tuple comprehensions, frozen set comprehensions, list comprehensions, and other stuff also don't really exist. All they were was just, again, we were making a generator, then passing that into some function, tuple, list, frozen set, or so on. So that is what we have been doing all this time. So again, list comprehensions have this syntax. This is pretty much equivalent to making a generator first, then passing that into the list function. So conceptually, whenever we say something like x, then comprehension, what we actually mean is make a generator, then pass that into x. It just happens that for some x's, say list or set or dictionaries, they have special built-in syntaxes. Okay, set comprehensions and dictionary comprehensions. Even though these things are equivalent to these, we still recommend that you use these instead, since, well, they're special built-in syntax. That's what this syntax is made for. Okay, so that's for generators and comprehensions. So let's go back to making more generators. So here we have a generator that takes in two sequences and gets their Cartesian product. Again, it's all possible pairings of each element in the first sequence as well as each element in the second sequence. So let us try making that. Define the Cartesian product of two sequences. Well, one thing we might try is, just like the other examples so far, we could have 4x in sequence 1, 4y in sequence 2, then all we have to do is yield xy. Simple as that. So just like how you would write this in a comprehension, we could have something like this. So if we have, let's say, list Cartesian product, then let's say 1, 2, as well as members. If we try calling this, we are going to get, well, these are the same as these, but for some reason, these next four are not in the list we have over here. So this is what we made. For some reason, this is wrong. Why is this not showing 2 paired up with each member? Why is that the case? So as we've seen, this only gives us the first 4 values. So the reason for that is, remember, these sequences can also be generators. Since the second sequence we're passing in here is a generator, inside this 4y in sequence 2, the first time we go over this for loop, it's already consuming the values inside this generator. So by the time x here becomes 2, members no longer has values it can assign to y, which is why we're only seeing these values over here. So to fix that, all we have to do is make this something other than a generator. So let's say we have sequence 2 is equal to list sequence 2. Here we're essentially preserving, quote unquote, the elements of sequence 2. You should also do this with sequence 1, since sequence 1 could also be a generator. So let's do that. Sequence 1 is also list sequence 1. So if we do that now, we will now get all of the values that we want. So again, remember that generators are always one-time use. Okay. So here we wrapped P inside a list. This is nice and all, but there are some instances in which you don't really want your generator to instantly generate all elements of T, especially if it's really long. Let's say T was something like my range 10 raised to 5, 10 raised to 10. This is a really big sequence of numbers. If you wrap that inside a list immediately, it would be extremely slow. As you can see here, we're getting a recursion error. So sometimes you want your generators to be what we call lazy. You'll see what we exactly mean by lazy when we go into one of the later lectures. And yeah, inside the practice set 7, you're also going to be asked to make lazy generators. So in order to know what lazy means, we will go over that in one of the later lectures, and you can also see what it means inside practice set number 7. Anyways, so these are two functions you can try implementing. So any and all are actually built-in functions in Python. They take in generators and return. For any, it returns true if at least one of the things is true. So let's say any true, false, true, or false, true, false, false. Since there's a single true, this evaluates the true. If this was false instead, this would evaluate to false. So this is any. All, on the other hand, works the same way, except it works like and instead of or. So it returns false if at least one of the elements is false. So here, it says that both any and all behave like this. Once any encounters a true value, it already stops, since it no longer cares about whether each of these remaining elements is true or false. Same thing for all. Once it already sees a false, it doesn't really care about what these remaining elements are anymore, since it already saw a false over here. So here we're asking you to make any and all short-circuiting, or for generators in general, we're asking you to make them lazy. Okay, so yeah, try these on your own. You can ask for help if you're stuck somewhere. Okay, and here, this is just showing you what any can be used for. So this mystery function makes a call to any in this conditional statement over here. As you can probably tell, since this kind of reads like English, what this function is doing is it's checking if any of the characters inside a word is a vowel, or in other words, if the word has any vowels. If so, it prints this, otherwise it prints this. Okay, so that is actually going to be our discussion for generators. So again, they are one-time use sequences. All this time, we have already been using generators. We have just been wrapping them around functions like list, tuple, and so on. So to practice generators, you can go over practice set 7. As for additional readings, Kuya Basti has an article here that goes deeper into what happens with generators and other things. You don't strictly necessarily need to know this for CS11, just like how you don't really need to know how hash maps work for sets and dictionaries. But it's a fun read. It's fun to know of. Okay, that's additional reading. So to do for this session, please practice. The mock hope and the hope are pretty soon, so hopefully you're practicing by now. So this is the accompanying official reference for this lecture. So that is going to be all for lecture 15. Thank you for watching.